Thank you, and sorry for the technical issues with the tablet and everything. All right, so this is the last part, and so the first thing that I would like to discuss a little bit more today is so the non-homogeneous fluxes. Now, as I mentioned before, this is a case where we essentially don't know anything in terms of quantitative regularity, and very little even in terms of compactness. So again, let me write down the equation. As I mentioned yesterday, I'm not going to consider derivatives on G or anything like that, just this for simplicity, and I will take A with divergence free in X. So that at least we don't have compression waves going in X. So this equation still propagates every LP bound as the one before. And again, for simplicity, typically what I will write down, I'm going to write down a theorem just in 2 minutes. I am going to consider a perturbation of the free transport. Okay. Something like that with B small. This is the main technical point, and once you have this, it's not super complicated. It requires a little bit of work, but it's not super complicated to extend that. To more general A of XV. Such that the gradient in V is nice, right? And the gradient in X is small enough with respect to the gradient in V. And I don't really want to write this kind of conditions here because, again, that would push us a little bit further into the technical discussion that I prefer to avoid. So I'm really going to focus on this case where this kind of expression is very explicit. And the kind of result that you can get here is the following. So I'm going to define the smallness parameter that will characterize everything. And And here it's typically something that you get in Fourier. Okay, so it's a well-known norm of the Fourier transform of B with where you pay with one derivative in X and one derivative in V. Okay. We'll get our usual assumptions. Right, so F in LP, G in LQ, and they are dual. Then the average, right, rule 5, the average in velocity is again in some L2 in time HS in X. And S can be any number, which is strictly less than 1/2 minus delta. Okay. So this is the kind of first result that you can get. So the interpretation is relatively simple. If delta is equal to 0, right, that means B is equal to 0, you get back to a purely homogeneous kernel, then S is equal to, can go up to 1/2, which is the regularity we had. The larger the perturbation, the more you lose in terms of the regularity. And if the perturbation ends up being too large, then you have nothing. And if you're going to do a perturbation analysis, this is obviously the kind of things that you should expect, because I have to remind you that there are conditions about, for an homogeneous kernel, there are conditions about how it can depend on the velocity. And in particular, if it degenerates, if it becomes constant in V, for example, then of course you don't have any regularizing effect. So B of XV could also simply be a B of V here. And if B of V is equal to minus V, then there's nothing. So, of course, you are going to have to assume that B is small in some sense, and the closer B is to V, the more problem you're expecting to have. So this sort of result is not surprising. Again, this is essentially what you would expect if you're going to treat A as a perturbation of the previous homogeneous kernel V. This is all right, so how do we prove that? How do we extend the method to prove something like this? Now, this is interesting because, again, I'm in the dual case, right? F and G are dual, so I won't need to do any complicated renormalization or anything like that. So the proof in that case is really a play with the multipliers. And so it's relatively simple. But we're using a slightly different multiplier than the one we had before. And so let me define now M, right, directly the multiplier in Fourier. Right. For some theta strictly less than 1. Okay. And the one I had before, right, the one that I had called K, is actually the one for theta is equal to 1. Now, the big difference here is the way it behaves, and it turns out that that particular M loses less than the multiplier we had before. Right, so if I'm looking at this term, which will give me the commutator, again, it's a very straightforward calculation, and what I get is the following. All right, so the advantage here is that I gain one derivative in x at the cost of one derivative in zeta. Okay. Because of course M was behaving, you see that since theta is strictly less than 1, M had a little bit of the derivative in V in it, right? Because that was 1 minus theta derivative. And here I'm using the 1, I simply divide by zeta to the power theta. Now, the big advantage with respect to the K is the K was losing more derivatives in velocity. It was losing 2 derivatives in velocity, and that comes to the degeneracy when you do this computation with theta equal to 1. You see that in the formula I've written, you wouldn't get anything. And again, that's because the dominant term cancels, and then you have to go down to a lower order term. Now I can calculate everything. Right, so it's the same type of calculation. I take the Fourier transform in X and V, and I put everything into the equation. And now if I split, again, A in A of xv is equal to v plus b, I will get, and I'm using this relation, right, I'm going to get something like this. Okay, so this is of course the term I like. There's a bad term here, which is the one that corresponds with V. And I get something like this, right? And again, I symmetrized everything, so that's why you see the real and the imaginary part, right, which avoids repeating the expression. All right. So the big thing now is, of course, to treat this B term. That's the one I have to handle. And this turns out with a little bit of symmetrization, I can write it relatively easily in the following manner. Okay, so there's no very big deal here. This is relatively straightforward, and now of course everything boils down to estimating the term like this, right? This difference of the m. Which, of course, since m is a rational fraction, is going to be expressed pretty much as being controlled by the corresponding derivatives in psi and in zeta. So it's relatively simple to calculate. And what you can get out of that, right, is are expressions like this. Right, so you write down what this is. You are doing a bit of a Cauchy-Schwarz, right? And you'll get something which is delta, the delta that was in the theorem, right? And then now, also, I don't want to give you the detail of the calculations. Again, there's nothing very complicated, but it's not the point here. The reason the delta is coming is, of course, when you're going to do the Cauchy-Schwarz, right, you're this f hat of psi prime and this f hat of psi, you're going to get an f hat square of psi multiplied by 1. So you're going to integrate something in psi prime, right? And the integral in psi prime is going to give you some L1 norm of b hat multiplied by some polynomial in psi and psi prime. You just have to track what is the polynomial, and that's what gives you this delta, where I remind you that delta is this expression. Okay, so no very big deal. Now we can go back to this equation. Okay, and I'm going to remind you that m, for example, m hat behaves like zeta to the power 1 minus theta. Okay. And that gives you a first estimate, which has the following form. So this term comes from the commutator with V minus that part here. And now this is going to be less or equal than a certain number of functions of f. So this is f hat at t equals 0 square plus f hat at the final time interval zeta. You're also paying with some sort of L2 norm in time of f. It's L2 of t and x, and it's h1 minus theta over 2 v plus the duality term that I haven't done anything with at this point. It's f at star g t theta. All right. So this is the first step, and of course you're not done, and you're not done because you see that if you're doing it like that, you are paying with those extra derivatives here in V, including there, because again, this is behaving like zeta to the power 1 minus theta. And the reason we have to pay with these guys is this perturbation argument, right? Because the control of B creates a term like that. And so when I'm using this, those formulas on B, I'm only losing one derivative in velocity. Right, I'm only gaining, if you want, one derivative in velocity in the now, because of course now we want to have as fast of a decay as possible, and I'm paying back with one derivative in x. So whatever I was gaining from the commutator has to fit exactly with what I have here, and I don't know how to do that if theta is equal to 1. So that is really the big the big constraint. Now, how does one conclude out of this complicated estimate? Well, you have to regularize in V. And you cannot do that immediately, and you have to be a little bit careful. And I'm not going to go again in full details, but so I'm going to, of course, consider now a different f, right? So I'm going, since I'm in Fourier, regularization just means that I'm multiplying by something, and the something that I am going to multiply with, again, I have to be careful with it. And what we found was working the best is this kind of polynomial extra decay, but of course, you don't decay too much. And you will want to take this R as small as you can, right? That's essentially going to give you the kind of gain of derivative that you have. So that's really, really, really essential that R is as small as possible, right? You are writing the equation on FR hat, apply the previous inequality to F at R, not F, and so in the end, you deduce the regularity of F hat, right? And you lose R derivative. From F at R. So again, the larger R, well, the less you get in the end. So this is not super difficult. It essentially means, again, having some sort of renormalization, which in Fourier is not extremely complicated to write down. So you will get an extra term, right? So the G here will contain a commutator term corresponding to the multiplication of this kernel. You have to estimate that commutator term, and that works in a manner that is relatively similar to the kind of estimate that I have derived here on B. And then you have to put everything together and optimize in R and in theta. And this is it. And this is it. So I don't know if there's any questions on this proof. Maybe in the end, if you want me to give a bit more details. So I think it is a great illustration of the method. And it shows how having something that is really quantitative, that consists in estimates, well, that allows you to do this kind of perturbation analysis. Whereas traditional averaging lemma approaches, you cannot do that because you don't, it's not that it's not quantitative, but it is that they rely on equalities on the equation. And therefore, perturbations are a lot harder to handle. Now, there's still quite a bit of work here to do and trying to understand. what happens if B is not smooth, for example, right? Then this method doesn't work very well. It's also a question of then what can happen, right? If B doesn't even have one derivative, then how can you say that you're close to V? But maybe there are other ways of interpreting averaging lemma, and so of interpreting the perturbation so that you don't need the smoothness of V. Don't know that. There are other potential applications of this kind of method. Another one that actually should work very, very well is whenever you have stochastic terms. That's again because having a bilinear approach, whenever you have Brownians, we're used to use directly Martingale's property, so throws out a lot of bad terms that would otherwise bother you. And so I think it's a very interesting idea that shows a lot of promises. As a sort of final conclusion, I wanted to mention also a variant of that we have started to look at with Toan and Nguyen. So this is not complete, but gives you an idea of also other ways of using this type of commutator methods to get dispersion. So this is an example of future work. So I'm going to go back to the nice homogeneous case, right? A of x equal to V. But now with some kind of explicit interaction. And here you can have a diffusion if you want, that actually doesn't make any difference. And rho, of course, as before, is the macroscopic density corresponding to F, so it's the average velocity. Now, I'm going to use repulsive kernels in the following sense. So K is the gradient of some V, which is the radial kernel, and it's repulsive, so V prime is negative, right? Now that is not strictly necessary, but again, to fix the ideas here, I'm going to assume that V has a very precise behavior, which is V prime, which is polynomial in X. Now, so this contains cases like that of Poisson, for example. And in general, it contains a lot of interactions with Riesz type of potential. So Riesz potential is when V is exactly equal to some polynomial X. And here is very interesting estimate. Okay. Okay. So what does that say? It actually says a lot, right? So it says that you get some sort of control in how characteristics in the equation can get closed in X. And that is due to those denominators, right? This X minus Y to the power theta, for example, tells you that if I'm following two different characteristics, right? They cannot really get too close, at least in an average sense, because otherwise this term would blow up. Now, you're asking me what kind of assumption I'm making on F initially? Nothing, right? So F could be a measure at this point, or any approximation to a measure, and you would still get that. So there's no regularity, there's no LP bound whatsoever of F that shows up in this estimate. The estimate is written here, the constants are actually explicit and do not involve anything else. And they only involve the constant C that is there in the bound on V. The first term here comes from free transport. The second term comes from the interaction between particles. So how do we prove something like that? Well, it's pretty much the same kind of idea that what I've been discussing before, and I'm going to define a kernel that in real space looks very, very much like the expression in Fourier that I was using before. And of course, it's because the V grad X, right, exactly corresponds to the psi grad zeta in Fourier. So V here is essentially playing a very similar role to what psi was playing, and X is playing a very similar role to what zeta was playing. In a sense, the commutator estimate that I had before in Fourier, that were dispersion in Fourier, now I'm going to use them directly in space. And if I'm calculating this, then I have an expression that is airily similar. And now what do? Well, I calculate d over dt of 1/2 of the integral of f against L convolved with f. And again, L is symmetric, so this is a very simple expression, right? Out of the commutator in velocity, I will get exactly this first term here. And then you have a false term, and the false term could be painful. But it turns out that if you use correctly the repulsive nature, then you can get an expression like that. So it has the right sign. And what about diffusion? Well, L is linear in velocity, so you know Laplacian V plays absolutely no role in this estimate. Can be there, cannot be there, doesn't make a difference. So this is a relatively straightforward calculation to show this proposition. And this is something that, again, we're starting on that, so this is the very first result. But it's something that already tells you a lot of stuff. And let me just show you two examples. If alpha is strictly less than 1, right? So remember alpha, 1 over x alpha is the behavior of the false term, right? If alpha is strictly less than 1, then we have the mean field limit from the system of particles to the Vlasov equation. With essentially zero condition on the initial data. The only condition we have is that the initial data has bounded moments, second moments in velocity and position, and you could even get rid of the momentum of the position. That would actually follow from the momentum. Yeah, so this is already a lot of fun because this recovers the previous result that we had with Fourier. With diffusion, and our method at the time could not handle diffusion. Now this is invisible, And again, we had a lot of conditions on the initial data, and here you had none. So how is this even possible? The point is precisely that you have a dispersive effect both in position and in velocity, because the free transport is dispersive and the interaction between particles is dispersive as well. So even if you do something really bad initially, which is like putting all of them in a small ball together, they will not stay like that. A second example of corollary is that this gives you long-term dispersion in Vlasov-Poisson. And that recovers the very famous result by Bardos and de Gaulle. Without any regularity on the solution. Now, if you're going to use that for Vlasov-Poisson, you still need to have enough initial regularity that you can give a meaning to the solution so that you can actually use the estimates, of course, right? But this is it. And it doesn't show up in the quantitative version. And the reason for that is we have a time integral here. I'm only going to write down one of them. And the time integral is controlled by a supremum in time. So if you have a good control on the kinetic energy, for example, right? I'm going to insist on V square. Then the integral of V square f dx dv is of course in L infinity of time, and what you gain is this time integral in exchange that shows that that term has to be small for a large time. Now you have to work quite a little bit more here to get to a precise result, but that's possible. So again, this is a different way of seeing this kind of commutator method. With pretty much a very similar idea. Again, now just something where I'm doing the dispersion in the real space instead of doing it for you. And so instead of getting averaging lemmas, I get something else, which is still a sort of regularity result, and something like that. And again, it turns out that because everything is very, very explicit, even if I have a false term, I don't necessarily have to treat that like a perturbation. And here the false term also gives me some dispersion estimates. So I'm not going to say more about that. I think it's enough. Thank you so much for having listened, and I'll be happy to answer any questions. Thank you. There was something in the chat, sorry, that I didn't see. Yeah, there's probably a DVDW everywhere. Yep. Yep, absolutely. I don't hear you, Mihai. I see that you're trying to speak. Yeah, now yes. I was saying the mask moves, so I was guessing that you were trying to say something.
Your thought consider the Black equation with some diffusion.
Mm-hmm.
And what kind of solutions are you using?
So that's a bit of a tricky question, as a matter of fact. So it's not absolutely. So it's not as easy to answer as it sounds. I'm not using characteristics or anything like that. So weak solution with enough regularity that I can handle every term are okay. And I can actually regularize this. L only has a singularity in X, as you can see. So I can actually regularize this, and so any type of weak solution where I can actually write down what the interaction term is going to work with that. The reason it's a little bit tricky is that this inequality itself can allow you to give meaning to some additional notion of weak solutions, which is not something I have said. But that's what's hiding behind the mean field limit. For example, that for alpha strictly less than 1, we could actually also use that to define weak solutions with F0 that is only a measure. But that becomes a little bit trickier.
Okay. And there's a Samir.
Yeah, I just saw it.
The main field limits for the kinetic Fokker-Planck equation with
No. So for this, it's, again, this is something that we are actually working on now. I wanted to mention it because it fits well as an extension of a previous method. So we have not written it down yet, and I'm actually still hoping to push that a little bit further than what I have written here. But in general, what I should say is that for the kinetic with diffusion, so Vlasov with diffusion, right? And singular forces, there's not a lot of results on mean field limits. And that's because a lot of the tools that we're using for second order system like Vlasov don't react super well with diffusion. So I was reasonably happy that here at least it seems that it's working well.
There's a question by Maxime.
Yeah. So this is true for any alpha. The proposition that you see on the slide now is true for any alpha. Again, as long as you can correctly define a weak solution. But the mean field limit, I don't know how to do it, of course. This is the other part of the question.
Hi, Pierre-Emmanuel, it's Maxime. I'm just wondering if there is a link with what you explained to us just before on some kind of hypocoercivity methods for this kind of equation.
Not directly, as far as I know. The big trick here is that you get a dispersion from the false term. which you could see as some sort of hypercoercivity, right? It's just in general hypercoercivity, you try to get it from the free transport and the diffusion. And here I'm keeping out the diffusion. Essentially, it doesn't show. It doesn't bother me. It doesn't help me. And so there is still some sort of nonlinear hypercoercivity here. Something I don't know, for example, is if you could use that to get uniqueness to the equation. This is working well because I'm using that f is positive. So uniqueness, you will need to handle the difference of two solutions. So it's not positive anymore, and so you need to calculate the Fourier transform of whatever shows up here. Plus handling the nonlinear term is more complicated. So I don't know, and that's one reason I'm not sure I would call that hypercoercivity. I think it's somewhat weaker than what people would like to see in a real hypercoercivity estimate.